Strengths of acids and bases. How strong? That is the question. How strong are acids and bases? Here are some strengths of acids and bases. Now, acids and bases are not all the same. Some are very strong and some are very weak. Some are moderate. And remember, the lower the pH, the stronger the acid. The higher the pH, the stronger the base. And here we have some very strong acids over here, and here we have some very strong bases, and some weaker acids and weaker bases. So strength. Strong acids and strong bases are strong electrolytes. That means they conduct electricity very well. There's a strong current of electricity in them. We're going through those solutions. It's because there's a lot of charge in them. So if there's a lot of charge, that means electrons can flow very easily. They fall apart completely. So strong acids, strong bases will dissociate completely. Weak acids don't completely ionize. So the strong acids will get more releasing of their protons, for example. The weak acids don't release that many protons. So we'll have a lot more ions in a strong acid, not as much in a weak acid. In a weak acid, we may just have this, but in a strong acid, we'll have all these. And if something is concentrated, we have much dissolved. Strong acids, strong bases, will form many ions when dissolved. Magnesium hydroxide is a strong base. It will fall apart completely when dissolved. So we'll get Mg2+, and then we'll have the OH and the OH. Complete dissociation makes it a strong base. How can we measure strength? Well, we have to know that ionization is reversible. We have this equation. We have the hydrogen with the acid going to the proton and the ion that lost the proton. So that will make an equilibrium. It goes back and forth between the acid and the dissociated ions. An equilibrium constant for an acid and acid dissociation constant. Now let's look at the equilibrium constant. So we already saw the equilibrium constant, just KEQ. We saw it for water, special case. Now let's look at for acid, Ka. Acid dissociation constant. How well an acid breaks up. Ka, acid dissociation constant, equals the concentration of H plus times the concentration of the dissociated negative ion, which would be the acid itself, over the original acid. So the stronger the acid, strong acids dissociate more. There will be more products. The stronger the acid, the more products. So if we have a strong acid, that means it's going to dissociate more into the products. The products will be heavily favored, not as much reactant. Now, if it's a weak acid, it doesn't dissociate much. It spends most of its time as the reactant, so it doesn't dissociate much. That makes sense. So that means you have a larger acid dissociation constant. And that makes sense, because if we do this mathematical equation, we're just going to get more concentration of this. That means it's going to be larger. Here it is again. Now here's some dissociation constants of weak acids. Remember that the larger dissociation constant means it's a stronger acid. Here we have some very weak acids, carbonic acid. And the strongest acid we see here is oxalic acid. So it ranges. This one, that means this dissociates much more. There's many more hydrogen ions, these negative ions, in solution. As compared with carbonic acid, we don't have as many hydrogen ions as we do with oxalic acid. Strong acid, if we look at this chart, we have the number of moles on this axis, and they're all the same for each of these graphs. But with a strong acid, we have complete dissociation. We have complete breakdown of acid, the donation of the acid, so we have hydronium ion here. Whereas with a weak acid, don't have as much hydronium ion. And look, there's absolutely no acid left here. None. Whereas with the weak acid, there is some acid left, and we get some partial breakdown dissociation into hydronium ion and A minus. Now, a very weak acid, we still have a lot of the original solution here, a lot of that original acid. You just get a very little dissociation. Not much at all. So again, we want a lot of breakdown to get a strong acid. What about the bases or bases? What about bases? Strong bases dissociate completely just like acids. It's the same concept. So here we have base plus water, and we get the BH plus and the OH minus. So the base, remember, takes the hydrogen. It's a proton acceptor, or you can say it donates the hydroxide ion. So they will dissociate completely to BH plus and OH minus. This is the base which takes the H. So the base dissociation constant is exactly like the acid dissociation constant, except it's with hydroxide. So notice that here, we're not putting water into the formula. We're just keeping it, the products on top and the reactant on the bottom. What broke down? Did that base break down completely to its components? So we can, again, we can ignore the water because its concentration does not change. Stronger bases dissociate more. Larger Kb, of course, will equal the stronger base. The same concept as with the acids, because we'll have more product. If the base grabs that proton, that means there's more dissociation, there's more product. It's a larger K. Let's try a problem here. We have 0.1 molar solution of methanoic acid. So the hydrogen ion concentration is 4.2 times 10 to the minus 3 moles per liter. We want to calculate Ka of methanoic acid. So methanoic acid is this, and it will break down into, we'll get rid of that hydrogen, plus C. Let's write the formula. Ka equals the products over the reactant product, and I have to make it bigger. Let's write what we have, or we're given, 4.2 times 10 to the minus 3, and this one will be the same because it's dissociated. If they have to be equal because they break down into equal concentrations. Now, it's not as though we can just put 0.1 moles per liter here, because this is the 0.1 moles per liter is what we started with, and this is after equilibrium. We want to know what Ka is at equilibrium. So it's not 0.1, but rather the equilibrium concentration of this, of methanoic acid, is the initial concentration, which is 0.1, minus the concentration of the ionized acid, which is 4.2 times 10 to the minus 3, because that's how much was lost after equilibrium. So now we just plug this into the calculator, and then we can figure out what Ka is. So that comes out to be 0.0958, and then we do the rest of the calculation, and then we get 1.8 times 10 to the minus 4. That's a somewhat weak acid there.